Hello friends, welcome back. Today we will start with our bilateral design. Still now what we are doing unilateral designs, okay? And in our last lecture we have finished the unilateral design part. So from today onward we will start bilateral design, and as I mentioned earlier also that bilateral design are the practical design approach. In bilateral then we don't assume anything like our S120 or not. We don't assume those things, and we assume it that our device is bilateral only. So in today's lecture I'll design the maximum transistor gain, okay, and then I will simulate that result in Serenade, and in my next lecture I will do the same example in ADS. So what is maximum transducer gain? We know that any time when we want to achieve the maximum gain, what we do, we just simply do gamma S equal to our gamma in conjugate and our gamma L equal to gamma out conjugate. This is the simple approach, and by this we can achieve the maximum gain. Okay, transducer gain, I have already explained the different type of gains we have. We have transducer gain, we have operating gain, we have available gain, and I know you might be having some confusion about those three gains. So in my next lecture I'll try again to clear all your confusion, but for now you just assume that in the maximum case our GT, which is transducer gain, is equal to our GP, which is not available operating power gain, and is equal to our GA, which is available power gain, and all other formula I have already derived in my previous video. So this is the simple approach. Then why I am making this video if it is so simple? It is not so simple because what we are doing for bilateral design, okay? If it is unilateral design, like if our device have S120, then we could have designed with this condition only, like condition will be true only for bilateral also, but we don't need to do anything because in unilateral our gamma S and gamma L are not dependent on each other. Why? Just recall the formula. What do we have? We have this formula. See, your gamma in is dependent on gamma L, and your gamma out is dependent on gamma S. Or in other sense, for designing the maximum gain, our gamma S and it's not equal, they are dependent actually to our gamma L from this formula. So what's the problem we'll face due to this formula? See, if you choose your gamma S equal to gamma in conjugate, right, then what will happen? Your gamma in will decide upon some gamma L because your gamma in is dependent on gamma L. Perfect. And your gamma S will define some gamma out. You can see here your gamma out formula directly coming from gamma S, so that gamma S will result into some other gamma out. And what we want to do, we want to take gamma L equal to gamma out conjugate. But see, we can't do this because there, like, we can do it, but simply we can't do it. We need to do some iteration, then only we can do it. So to simplify those approach, what we do, see, we have two equations and we have two unknown. Basically we have two unknown, gamma L and gamma S. So we can do it as quadratic equation approach, which we have learned in our schools, okay? So exactly same in this microwave amplifier design also, we take the approach of quadratic equation. We define our gamma S and gamma L as follows. See, this is your gamma S, and why I have given one M, because for maximum gain, and gamma L, same M for maximum gain. And these are, you can recall, these are all coming same as our quadratic equation only. And our V1 and V2 and C1 or C2 are this. And I know you are getting overwhelmed with this much of formulae, but we don't need to remember any formulae. and you can easily derive this thing. Actually, if you just recall how we did in our school, how we did for our quadratic equation, same thing we are doing here, only just here we are dealing with s11 s22. So I'm not doing it again because it could consume our time, so I'm not doing it, I'm directly stating it here. And it's not important also to derive those things, you just need to see this thing. Okay, so this is your transistor gain formulae, and what we are choosing, we are choosing gamma in equal to gamma s conjugate and gamma out equal to gamma L conjugate, or vice versa. Okay, so your new GT will be in this form, correct? We just replaced our gamma S with the gamma MS, which we just found out in our last slide, and gamma L with the gamma ML. And as these two are conjugate to each other, we can come up to this formula, up to this formula. Okay, and if we do some more manipulation, which obviously I am not doing here because it's not necessary, then your GT max could also be written in the form of K. And I hope you remember what is your K. K is your one of the condition. K should be greater than 1. One of the condition for your unconditional stable devices. Okay, so K is the same. Actually, we just need to do some manipulation, but it's not necessary, so I'm not doing it again. You just need to know that yeah, your GTmax is also dependent on K. Okay, so see, K equal to 1, K less than 1, and K more than 1. K equal to 1 is the partition where your stability and instability are defined. Okay, so from this equation we again define another term, which is maximum stable gain. And maximum stable gain, when it will be maximum stable gain, when our K is in the partition of or marginally stable, it is equal to 1, K equal to 1. So if I put K equal to 1, then I'll get G MSG as S21 by S12. And actually we use it when our device is not stable. It is used as the figure of merit for that device, because we can achieve maximum up to this gain with a stability in our consideration. Okay, so let's proceed to our example and let's understand, like, work around this much of formula. Because if we have some software, then we don't need to put any effort, and we can get out our result. But if we don't have commercial software and we have only Serenade, like during our college days, we need to design it with Serenade only. So in Serenade we don't have so much of liberty of automation of this much of formulae, and we need to do what, we need to calculate them using our calculator. But we have the Matlab, and if we have the Matlab, then we don't need to calculate it in our hand, just need to define this formulae and Matlab will do these things for us. So this is our example. We need to design a microwave amplifier with frequency range of 6 gigahertz. We have provided with the S parameter file, and these are the S parameter for a single frequency, which is 6 gigahertz. And one thing you might need to know, that this is a FET device. Perfect. So how we find out the S parameter? Actually, how we find out the S parameter, what we do, we bias it. Okay, we do the some biasing. uh, we do some biasing here, like this is your RF choke to choke your RF, because we don't want RF to come to a DC part, and we give one DC block here, and they are as ideal as possible. Okay, and this is your RF input. And here what we do the same thing for our drain bias. Sorry, I'm doing the opposite way. Okay, this is again your RF choke, and here we grounded it. So we give RF through this port and we take out from this port, and by this way we have two port, and if we have two port, we can find out using our VNA, vector network analyzer. We can find out our S parameters. Okay, so here what they did, they given us S parameter, and then they given also the biasing condition, like your VDA should be 4 volt, and they have given the current. Okay, so that means for this much current, how much gate bias we need to calculate it. Okay, so if we want to design it our RF board, what we do, we just purchase this thing and we put it in our RF board and we keep the same biasing conditions, and then we apply the matching circuits. And why we need to apply matching circuit? Because we are defining our gamma S and gamma L, and gamma S or gamma L coming because we need some specific gain, and for that specific gain we have calculated our gamma S and gamma L. And if we match our input and output of our device with respect to these values, then we will get the exact gain which we need or which our employer need from us. So that's why we do this much of things. So let us recall what we need to do. We need to select a device which is already done. We need to see the stability, which we will see. If it is not stable, we need to stabilize it, and we know how to stabilize it using our resistive loading. Then we need to see if we can simplify our design using unilateral figure of merit. And I have already discussed in my last lecture. If it is okay, like if our unilateral figure of merit are valid, then we can directly choose gamma in equal to gamma S conjugate and gamma out equal to gamma L conjugate, and our gamma S our gamma in will be simply S11 and our gamma out will simply be S22, because in our gamma in formula we have something here also, but we have a S12 term, and if we assume our device is as unilateral, then this part will vanish. Okay, same is true for gamma out, so it's simple. But if our figure of merit is not valid, then what we need to do, we need to do for maximum gain, as we are designing it for it is written for maximum transistor gain. Okay, so for maximum transistor gain, what we need to do, we need to find out our B1, B2, C1, C2, then from that we will get our gamma ms and gamma ls, and if we get these things, we can directly go to our Serenade. Actually, before going to Serenade, we need to match it using our Smith chart, and after getting those length of our stubs, length of our transmission line, we can go to our Serenade and we can simulate it. Okay, so we'll do this interesting thing today. And before doing this, if you are watching it still now, then please subscribe to my channel, because I am very close to 100 subscriber, and for me it's a very big milestone. So please help me with your one subscription and motivate me. Okay, so let's do one thing. Firstly, get these values. And so for getting this value, what I did, I wrote a Matlab script, and I know you want this script to be in your description, in my description. Okay, I'll give it to you, but please try to do it on your own and then compare with my file. Okay, and if you did it on your own, please comment it out below that yeah, I have done it on my own. Okay, so in this script, actually I am not going to explain every line, because in my lecture 9, you can see the I button. My lecture 9 link will be there. In my lecture 9, I have already explained many things of this script. I will explain the extra thing which I am doing in this script. Okay. So firstly, I am giving feeding the S parameter which is given in my questions. Then I am finding out the stability analysis because I want to do it. Then this is extra, I am doing the unilateral design check if my figure of merit is valid or not. And then what I am doing, I am doing those things, my beta b1 b2 c1 c2, I am just giving the values here. Then yeah, one thing, please see your formula for beta 1, not beta 1, your gamma s. See, your gamma has a plus and minus, so your gamma s could be a positive and could be a negative, so which one you will take? So the easy thumbs rule is take any one which is less than 1. So your positive or negative one will be less than 1 and another will be more than 1. And as we are designing for stable circuit, so our gamma s or which is gamma ms should be less than 1. So take which is less than 1. There are some things which is bit complicated in the book, in the Gonzalez book, but I am not discussing those things. Just take which is less than 1. So that's why what I am doing, I am defining gamma as positive, negative, gamma ml positive, negative, and then this thing will be in complex form. So I need those things in my magnitude and angle form, because I'll put this gamma s. Don't confuse between gamma ms and gamma s. They are same only. Gamma ms is the maximum gain possible from our gamma s. That's why I'm telling it in gamma ms. Okay, so we'll put this gamma ms to our Smith chart, and to put in our Smith chart we need the magnitude and the angle. I'll get the magnitude and then how much angle I need to rotate for my gamma ms. So that's why I'm converting this thing to our magnitude and theta form. And again, what I am doing, see, I am printing those things, and when I am printing the theta I am multiplying something, because in Matlab by default it is in radian form, and I don't know how to change this default actually. If you know, you comment it out. So I don't know, that's why from default radian I am changing it to degree form, because our Smith chart is in degree form, so I need it in degree form. That's why. And then lastly I am using the maximum GT possible. So I'll see this result, and I want to see when I'll derive it in my Serenade, I need to get out to exactly same value, because maximum GT possible and we are designing it for maximum gain, so these two things need to be coinciding. So that's why I am doing it here. So if I run it, so see, uh, my delta is less than 1, my k is more than 1, and my mu is also more than 1. So my device is stable, I don't need to do anything. It's okay, great. Then value for u is your figure of merit, and if I put my figure of merit in my formulae, then I can get a, like if I assume my device is neutral, then I can assume a error from minus 0.89 to around 1 dB. Okay, as in the example they have not given any figure of merit, so what we will do, we don't assume it as a unilateral device. If they say like error of 1 dB plus minus 1 dB we can tolerate, then we can direct go to unilateral design case. But as they have not mentioned, so we will just ignore these things, and we will find out our gamma is positive, gamma is negative. And see, positive is your more than 1 and your negative 1 is your less than 1. So we'll take the negative 1, and same case for gamma L, negative 1. And what the gain we can assume, like we can expect it is 11.38 dB. So we will verify it when we'll do in our Serenade. Okay, so one thing got sorted. Now what we'll do, before going to matching part, I know maximum of you know how to do matching in using Smith chart, but still a quick review. You can skip this part and you can go to next part. But those who don't know how to do matching, if you don't know, you need to revise your Smith chart obviously, but those who want to a quick recall, they can continue to this section. So our gamma s is around 0.76, it is around 0.76, and it is around 177 degrees. Okay, our this is our gamma s 177. Just remember it, and let me go to, yeah, this is our Smith chart. So see what we do, we know our gamma s, because firstly we'll do it for gamma s for our input part, and then we'll take the gamma l for our output part. So for input part, our gamma s or ms is roughly 0.76 and 177 degree. So 0.76, how we take it, see, here in our Smith chart, here we have some scales, and using our scale we'll choose zero point 0.7 something, 14 or something. We'll have our compass, and we can draw a circle here with same radius. Okay, so wrong circle, same circle. Okay, and then we have given with the angle, so we'll find out where is our 177 angle, and it is around here only. So this is your gamma ms point, right? And we will design this using shunt stub, open or close. And if we do something in shunt, then the thumb rule is that we do it in our admittance chart, and it it is our impedance chart. So admittance chart means go diagonally opposite to the opposite side of your Smith chart. If you don't know your Smith chart, you will get confused here, but you know, if you know it and you just want to recall, then you can get it. Okay, I'm assuming you know your Smith chart. Please, I'm sorry, I'm not explaining it here, but definitely in my future videos somewhere I'll give one playlist about Smith chart. But now, for now, you can search Google and you can find many good courses on Smith chart. Okay, so we'll go there, and our 50 ohm is here, so we want to match this thing. So matching could be easy because we can go here, like this is your source and we want to come here. Okay, and from here we want to see a gamma x of 0.76 and 177, and in my video I'll give it in my I button, in which video I have explained the load versus generator, that doubt. Okay, so you see that if you have doubt, then you click on I button. So this is our generator for now, because we are seeing this gamma s which is generating by this MOSFET. Okay, so that means if we go from this part to this part, then we will have an anti-clockwise rotation in Smith chart, and if we go this way, then will be a clockwise rotation. So we are starting from 50 ohm line, like 50 ohm point or matching point. That means we are starting from here and we are going toward this way. And rotation we do in our Smith chart when we rotate in our constant VSWR circle. So this is your constant gamma circle, right? So from here to here, how we will reach? We will reach using a stub, and that stub should have a value. That stub should have a value. Some, this is rough, so don't take it granted. And if it is not rough, then our from here to here, because what we are doing, our real part is constant, real part is 1 only, but we are adding some j part, and that j part is around 1.4, 1.3. The j part is around 1.3, so we need to put a stub to add this value j 1.3. Okay, and after reaching here, and if it is a short stub, it is a, if it is a open stub, then we have open and short. I'm not explaining those things here again, because it's not a Smith chart matching lecture, that's why I'm not defining those things again. And from here to here we have two options, anti-clockwise rotation or clockwise rotation, but as we are moving toward our generator, so we will have a clockwise rotation and we'll reach here. Okay, so if you don't have anything, not anything, if you don't have ADS or those commercial software, and if you do it using a Serenade open software, Serenade free software, then this part you need to do manually in your paper Smith. But I am not doing it, obviously, because it will take some time, and I am taking it directly from the book, that screenshot from the book. So see, we got some gammas here, and we need to go diagonally opposite, and we came here, and this part is your stub length, which is adding the imaginary part 1 plus j something, and then this part matching your circuit, and this is the anti clockwise movement because we are going toward our generator. So we can realize this imaginary part using a short stub or a open stub. If it is a short stub, then we need to start from here. The length of our stub should be from here up to here. And if we use a open stub, then our length could be from here, because this is the open circuit end. So we got a length of 0.185 lambda, and how we're getting it, because this circle, these are the lambda. Okay, so if you able to read your Smith chart, you can directly get the length, and here also we are getting the transmission line length. They are all directly, and getting something in the form of lambda is very good, because when we design any transmission line, what we do, we design it for our theta, and our theta is beta L, and our beta is 2 pi lambda and L, and L is in your in with respect to lambda, so that means 2 pi lambda, and this is 0.185 lambda, so lambda will get cancelled, and if you multiply your 0.185 with 2 pi, then you will get the your stub length in degree, and we can easily do this thing in our Serenade very easily, and we can design the amplifier. Okay, so same thing we are doing for our output part also. You please verify it, you please verify this matching part here also. Same thing, we will get our ml here somewhere here, and we will go directly opposite part here, and then we will add the imaginary part, and then the transmission line part. Okay, and this thing just keep watch. We maximum time students do wrong here, they take up to here, but you don't need to take up to here, you need to take up to here. Okay, and if something you are getting here confusing, you just comment it out, I'll try to answer those things, or I'll make one video to explain the Smith chart matching part. Okay, so I'm not doing this thing here again, because I want to design as quickly as possible in our Serenade. So let's open our Serenade. So for simulation in Serenade, we need the S2P file, and I have already made that S2P file from our question, and I have explained how to make it. It's simple. You can make it in Notepad. Okay, so I'm not explaining it here. So we have already made that one. So this is your Serenade. So what we want a S2P port. So for S2P port, come to parts, and you can see black box and with two ports. So we need it port, we need to give a device name. Okay, so one thing you need to keep in your mind in Serenade, your file name and device name should be similar. Your file name will have some extension .s2p, but your device name will only have the file name without the extension part. So let's select the file in question. They have not decided about the which substrate we need to use. Epsilon r nothing is mentioned. So what we'll do, like we can go to tools and we can design our transmission line, but as they have not given anything, so we'll work with ideal part, and these are the ideal. So this is your ideal transmission line, this is your ideal open-ended. So we want one open-ended, so that take this, and for your example I have already one playlist on Serenade. Okay, so you can go there and check if you don't know how to do this thing in Serenade. I'm finding out the calculator because I want to multiply my lambda value. Okay, so what is it's 0.185 lambda. Okay, so it is 0.185 into 2 pi, and 2 pi in degree 360, so 0.185 into 360, and it is 66.66. So 66.66, I hope I'm correct. 66.6 your E, your frequency is 6. Frequency is 6 gigahertz, and we need to write it here. And our Z system defined on 50 ohm. If it is not given in the question, it will be by default 50 only. Okay. Then I need a transmission line. This is a transmission line. And what are the value for transmission line? It is 0.0615. 0.0615 into 360, so it is 22.14. 2.14, and your Z will be 50, and your frequency will be 6 gigahertz. Perfect. You can copy this thing to here. Now what is this transmission line? It is 0.169. So 0.169 in 360, it is 60.84. 60.84. And last but not least, it is 0.176. 0.176 into 360, and it is 63.36. 63.36. Now we need to take ports 150 and port 2 and our wire. Then we need to take the frequency generator, and frequency generator, let's keep it only 6 gigahertz, because we had this information only with us. And let's analyze. So you can see this result, and you can see the marker. The gain is around 11.37, and it is same as we got from our Matlab code or the formulae for the GT max. So that's all for today, and in my next lecture I'll do the same example in ADS.